What is the theory of relativity? So, the theory of relativity essentially is a theory of gravitation, a theory of gravity. So, relativity came in two phases. In 1905, Albert Einstein put forth the special theory of relativity. And in a decade later, after a great deal of work, he put forth the general theory of relativity. So the general theory of relativity builds upon the the very baby steps he took in the special theory of relativity. So I'll talk about the general theory of relativity, which is what relativity actually is. So until this theory came around, we understood gravity reasonably well. We had the Newtonian theory of gravity, which sees gravity as a force that acts at a distance, a force that acts at infinite distances instantaneously. So it's an instantaneous force. No matter how far you are from a massive object, you will feel its gravity. No matter how far you are, you'll feel it instantaneously. That is how Newton's law of gravitation works. If you can see the equation, so that is how we understood gravity. Now, general relativity says that gravity is not a force, it is the geometry of space itself. It is the curvature of space time. Mass causes the fabric of space time to curve, and this curvature is what we interpret as gravity, as this so-called, as this apparent force of gravity. So according to this theory, the entire fabric of the universe is a four-dimensional fabric. It's called space-time, three dimensions of space and one dimension of time, all integrated together. And that is what we are immersed in. That is the stage or the arena upon which the universe exists. So that's space-time. And everything in space-time has a limit, a speed limit, which is the speed of light. So that is something that's hard coded in the universe. Nothing can travel faster than the speed of light, not even these ripples in space-time themselves. Even these ripples in space-time will only travel at the speed of time, at the speed of light, I'm sorry, and not beyond that. So that is a very interesting effect. It's a very significant difference from what Newton said. So let me illustrate this by doing a thought experiment. So this here is a toy model of our solar system. We have the sun at the center and all the planets around it. The sun should be much smaller, but you get the point. So according to Newton's theory, this star at the center, right? The star at the center here, it exerts a force, an attractive force on all of the planets, and it's an instantaneous force. It's a force that acts all the way out to infinity. Now let's assume for a second that, let's do this thought experiment. Let's suddenly switch off the sun. The sun suddenly disappears all of a sudden for whatever reason. It's a thought experiment. We can do anything. So let's assume that I switch off the sun, I make it disappear. Then what happens? These planets are all going round, mostly round around the sun. And since the sun disappears, this force it was exerting on all the planets instantaneously disappears. And what will happen is all the planets will fly off in all directions, right? That's what will happen instantaneously. At the same time, all the planets will disappear, will go off in all different directions in various parts of space. That's what will happen according to the Newtonian theory of gravity. Now, according to Einstein's theory, general relativity, if the sun were to disappear, it would take 8 minutes for Earth to know about it, because the speed of light says that it takes about 8 minutes, roughly 8 minutes, for light from the sun to reach the Earth. So if the sun were to disappear, we would not know about it for 8 minutes. And it's only after 8 minutes that the gravitational effect or the sudden gravitational disappearance of the sun would have an impact on us. So it's only after 8 minutes that the Earth would fly off, and it would take longer for the other planets like Jupiter and Saturn to know about the fact that the sun has disappeared. And only then would they start flying off in different directions. So that is the difference, my friends, between Newtonian gravity and general relativity. General relativity, like I said, it treats the fabric of universe as a four-dimensional space-time, and this is the difference between general relativity and Newtonian gravity. General relativity is much more accurate than Newtonian gravity. We can still use Newtonian mechanics to send a rocket to the moon and bring it back safely. We can send people to the moon and bring them back safely without using general relativity, using just Newtonian mechanics. So it is pretty accurate. But there are certain phenomena that it can't account for, and that is where general relativity comes in. It is an improvement, a significant improvement on Newton's theory of gravitation. So that, in very brief, is what relativity is. It is a theory of gravitation. It is an improvement upon Newton's theory of gravity, and things such as GPS and much more would not have been possible had we not discovered general relativity.